What is up, my people? This is Mr. Tui, creator of the Digital SAT Crash Course series. And in this video, I'm going to teach you another one of the most powerful strategies you can apply right now to get a massive score increase on the Digital SAT Math section. And that strategy is plugging in the values in place of the variables. In part 2, I'll teach you everything you need to know about functions, one of the most commonly tested concepts on the Digital SAT Math section. Oh, and by the way, if you like this video, you definitely want to get access to the full version of the course. Just click the link in the description below to access the full version. In the meantime, sit back, relax, and enjoy Day 2, Part 1 of Digital SAT Math Crash Course. Let's jump into some new questions. But before we do that, I want to go to the rules for SAT Math real quick. Can you see that on the screen share, ladies?
Yes.
Okay.
Yes.
Good.
Yes.
And Catherine, I'd love you to read rule number 1. This is what we're going to focus on today. I know we start with rule number 2, which is kind of weird, but there's a reason we start with the Desmos here, because we're going to combine rule number 1 and rule number 2 today. Go ahead and read rule number 1 for us, please, Catherine.
Rule number 1, avoid algebraic operations whenever possible. Instead, plug in values for the variables and solve.
Yeah, I think the most useful strategy, the most powerful strategy so far that I've seen on the digital SAT is that using that Desmos calculator. But if you can combine rule number 1 and rule number 2, plug in the values in place of the variables, and do it with the Desmos, combine those two rules, you're going to be unstoppable on this test. And that's why I started with rule number 2, is because some of these plugging in values questions, you're going to want to use the Desmos. You're going to want to be able to navigate your way through the Desmos first to be able to do that. So I want to practice that avoiding algebraic operations and plugging in values in place of the variables on some of these questions. So I'm going to bring up a new question up here on the whiteboard. And Catherine, I'll have you solve this one. All right, go ahead and read question number 1 for us, please.
Tilly earns P dollars for every W hours of work. Which expression represents the amount of money in dollars Tilly earns for 39 W hours of work?
Ooh, what do we solve for here, Catherine?
We're solving for the expression that represents the amount of money Tilly earns for 39 W hours.
For 39 W hours of work, whatever the heck that means. Now, I don't know if you're anything like me. When I saw this question the first time, I read this and I was just like, wait, what? Like, what does that mean? What does 39 W hours of work mean? This question just kind of went over my head, and I didn't fully understand it. There's like 2 different variables here. We got a P and a W, and they're asking for how much money she earns for 39 W hours of work, and like I just didn't quite understand it. Does the question make some sense to you at the moment, or maybe not so much, Catherine?
A little bit. Like when I first read it, was really confusing. But if you like read again and again, you can kind of get it.
Kind of, right? Yeah. And what about you, Ruby? I mean, does this question make some sense to you? Do you think you ladies know how to solve this one, or not so much? Right now, just looking at it right now, thinking in terms of the variables and the algebra here, does this make some sense to you, Ruby and Emma?
I think I would be able to, but word problems always mess me up.
Yeah.
When there's so many things to look at.
Yeah. And
most of the time, not all of them are useful.
Yeah.
So.
Yeah, it's just this one is just kind of confusing, and it's funky because this is like question number 1. They generally start with some easier questions on the modules, but like this one just still confuses me. We don't know what P and what W is, and that's I just don't really know how to structure this expression sort of algebraically. I still don't right now. I'm sure there's a way to do it, but like it's just not obvious to me. I don't think it's obvious to most of the students I'm working with either. So let's do this. Let's practice the strategy of plugging in values in place of the variables. Because anytime you see variables in the question, especially when we see them in the answer choices, there's generally a way to create values for those variables, and we're going to make it really concrete and just really easy to understand if we create reasonable values. So let's do that. Let's practice that. Catherine, I want to create a value for P. Okay, now P is the dollar she makes for every W hours of work. So let's just pick a reasonable value here for some number of like dollars per hour that she's making. Does that make some sense here?
Yes.
Okay, so give me a value for P. How many dollars per hour is she making?
15.
Great, $15 an hour, right? Wonderful. Okay, so she's making $15 for every W hours of work. But if we're talking about like dollars per hour, $15 per hour, then we know what W is going to have to be. What's W going to have to be? If we're talking $15 per hour.
W's going to have to be 1 hour.
W's going to have to be 1 hour. So we could literally reread this question right now. It's going to make a lot more sense. Tilly earns $15 for every 1 hour of work. Does that make sense? Can you wrap your head around that now?
Mm-hmm.
It makes perfect sense. Now, the question is, which expression represents the amount of money in dollars Tilly earns for 39 W hours of work? But if W is 1, this is for 39 hours of work. Does that make sense? How we can reread that as 39 hours of work if W is 1? And you can say no if it doesn't.
Kind of. It's still a little confusing.
Well, if W is 1, then basically this just becomes 39 hours of work, right?
Yeah.
Right? And it's really easy to, if she's making $15 an hour and she's working 39 hours, you can calculate how much money she's making, right?
Mm-hmm.
How much money is she making? How would you calculate that?
If she was making $15 an hour?
Yeah, if she's making $15 an hour and she works for 39 hours.
You would just multiply it by 39.
You just multiply them, right? And we can bust out that Desmos. Or if you got a little iPhone calculator, that'll work too for right now. But I'm just going to punch in Desmos, and we're going to get 15 times 39, and we'll figure out how much money she's making. She's making $15 an hour, working 39 hours. She's making $585. Does that make sense so far?
Mm-hmm.
Okay. So 585, I'm just going to mark that here on the screen. And then the right answer has to give us 585 when P is 15. Does that make sense?
Yes.
Yeah.
Yeah.
Yeah. Ruby, Emma, does that make sense as well? Why the right answer's got to give us 585?
Yes, that makes sense.
And if you're just looking at the answer choices, I mean, we're going to plug in a 15 for P. But I'm looking at these, and I think I know what the right answer is when I'm plugging a 15 for P. This is one answer that shows us what we did. Catherine, what's the right answer here?
Is it A?
It's got to be A. It's got to be A. 39 times P. Right? 39 times 15, if P is 15. It's the only one that gives us the calculation we did. It's not going to be B. B is going to be too small. C is going to be too small as well. And D is going to be negative if P is 15. So it's got to be A. And it is. Does that make some sense, Catherine?
Yes, it did.
Yeah. Yeah. Look for ways to start thinking in concrete terms by plugging in values in place of the variables, maybe especially on word problems. And it's just an easier path. Like, I'm still not quite sure how to set this up algebraically. I'm really not. It's just tough to wrap my head around. There's a way to figure it out, I'm sure. But it's just easier if you just plug in values in place of the variables. You'll get it right. Questions about that?
Nope.
Okay, great. Ruby, Emma, any questions about this?
No.
Okay,
Nope.
Let's keep practicing. All right. All right, I've got another question up on the screen. Go ahead and read number 15 for us, please. Ruby, you're up.
Okay. The equation that
Yeah.
is the estimated number of employees at a restaurant, where T is the number of years since the restaurant opened. Which of the following is the best interpretation of the number 5 in this context?
Ooh, what are we solving for here, Ruby?
I guess just which of the following solutions below is the best interpretation of 5?
Yeah, that's it. What's the best interpretation of the number 5 in this context? That's the question.
Okay.
What does 5 mean, right? That's the question. And we see it here in the equation, in this function. We see 5. What does it mean? Now, I'm guessing, just by looking at this equation, this function right here, it's not super obvious what 5 means. Is that a fair statement, or do you understand what 5 means there? Maybe you do.
No, I do not understand.
Yeah, but most students know that. Catherine, Emma, can you look at that and just kind of figure out what 5 means in that expression, or no?
Well, is it like a constant?
It is a constant. It is a constant. But that's not one of the answer choices as well, right? They're getting real specific about what 5 means. And I just don't think it's super, super obvious to most students looking at that, okay? So let's practice this strategy of plugging in values in place of the variables. I think we're going to be able to figure out what's going on in this function, what things mean. I think we can figure it out. Okay, so let's do this. Let's create some values for t. And we're just going to plug them into the function and see what happens. Okay, but let's make it really clear. What does t mean in this function, Ruby? What does t mean?
T is the number of years since the restaurant opened.
T is the number of years since the restaurant opened. Okay, so I want to start by plugging in a 0 for t, just to see what happens, okay? Now think about what this means. It's not just that t is 0. Yes, t is 0. But what does it mean if t is 0? Ruby, what's it mean?
It means that it's been 0 years since the restaurant opened.
It's been 0 since it opened. It's basically like right when it opens. No years have passed. Does that make sense?
Yes.
Or if t is 1, that means 1 year after the restaurant opened. We're going to test that as well here in just a moment. So think about what it means as well. And if we plug in a 0 for t, what do we get for e? And I guess e, that's going to give us the estimated number of employees, right? When t is 0. That should. Does that make some sense?
Yes, I think so.
Okay. So let's plug in a 0 for t. And here I'd use the Desmos calculator. I mean, you might be able to sort of, if you know how exponents work, you might be able to sort of do it mentally, but let's not mess around with it. Let's plug it into Desmos. And so it's going to be 5 times 1.8 to the power of what? To the power of what, Ruby?
0.
To the power of 0, because t is 0.
Yeah.
And what does that give us?
5.
It gives us 5. Interesting, right? That surprised some students. A lot of students think you're going to get 0. Things to the power of 0 aren't 0. What is anything to the power of 0, Ruby? Do you have any idea?
Doesn't it just cancel out the number that it's like connected to?
It's funky. Anything to the power of 0, listen carefully. Anything to the power of 0 is 1. Anything to the power of 0 is 1. And again, you know, I used to have like students like really memorize that, and they had to really have that understanding. But like once again, with the Desmos, you don't even need to do that, right? You just punch it in, and you'll figure it out. I mean, anything to the power of 0 is 1. If I get rid of the 5 here, 1.8 to the power of 0 is 1. Doesn't matter what, anything to the power of 0 is 1. Be aware of that. That'll kind of make sense of the expression, but again, just punch it in Desmos, and you don't need to worry about it. So we get 5 times 1, and that's 5. So we can interpret what that means. That means when no time has passed, there's 5 employees at the restaurant. Does that make sense?
Yes.
Okay, that might be enough to give us the right answer. I think it is, but I want to practice this again. Let's plug in a 1 for t. I just want to see what happens. So, let me erase this real quick. We'll make t equal 1. So now think about what this means. This means 1 year has passed. Okay. And let's punch into Desmos and see what we get. So we got 5 times 1.8 to the power of 1. Do you see what that gives us, Ruby?
Yes.
Yeah, we got a 9. So that means after 1 year after the restaurant opened, we've got 9 employees. Does that make sense?
Yes.
Okay. So that's an increase of 4 there. Okay. But I just want to show you this. We can plug in a 2 and we'll get another increase. You know, we should. We will. But I think this is enough to give us the right answers. Let's test these answer choices right now, just based on what we know. We know after no years have passed, we got 5 employees. After 1 year's passed, we got 9 employees. And we're looking for the best interpretation of the number 5. Go ahead and read answer choice A for us, please, Ruby.
The estimated number of employees when the restaurant opened.
Is that the best interpretation of the number 5, or a possible interpretation of the number 5?
No.
Why not?
Because hold on, I'm trying to think of a way to say this where it's not confusing.
Yeah. What is the number of employees when the restaurant opened? We know it.
Yeah.
We know it. What is it?
It's 5.
It's 5, isn't it? So could that be the best interpretation of the number 5, the estimated number of employees when the restaurant opened?
No.
I think it could be. Because that's what this is right here. When t is 0, that's when the restaurant opened. We got 5 for the number of employees. Does that make sense?
Maybe.
Well, let's see if we can focus on elimination here. Hold on. Go ahead and read answer choice B.
Okay. The increase in the estimated number of employees each year.
Is that the best interpretation of the number 5?
No, that one's not.
That's definitely not right, because we just tested this and we saw after 1 year it goes up by 4. After 2 years, it's going to be even bigger. I'll show you why here in just a minute. But it can't be B at the very least. You might be like maybe or iffy about A, but we know for sure it's not B. What about C?
The number of years the restaurant has been opened.
Is that the best interpretation of the number 5?
Also no.
Also, no, yeah, because t can be anything, right? Could be 0, could be 1, could be 2, or it could be 5, but like, could be anything. It's a variable, which means it varies. It's not 5. What about D?
The percent increase in the estimated number of employees each year.
Is that the best interpretation of the number 5? Is it a 5% increase?
No.
No, it's not a 5% increase. It went up from 5 to 9. That almost doubled. That's almost 100% increase, not quite. So it can't be D. So you could also think in terms of elimination here. But do you see now why 5 is the estimated number of employees when the restaurant opened? Do you see that now, especially when we plugged in that 0 for T? That tells us how many there were. When it
okay. Yeah.
Does that make sense now? Yeah. Emma, Catherine, does that make sense why answer choice A is the best answer here?
Yes.
Yeah. And even again, if you're iffy about A, you're like, I'm not certain about that. And remember, I asked you like why it wasn't A, and you couldn't really give me a good reason why it wasn't, which is interesting as well, right? If you don't have a good reason to get rid of it, don't get rid of it. But when you look at the others, you're like, well, that can't be right. It's not the increase. It's not the number of years. That's a variable. It could be anything. And it's not the percent increase because it's much bigger than a 5% increase. It's closer to a 100% increase. In fact, I think it's going to be an 80% increase. We'll talk about why. We'll get into more detail about percent increase and decrease on day 3. But does that make some sense why A is the best, ladies?
Yes, it does.
Yeah. I mean, if you wanted, you could plug in a 2 as well for T and just see what happens. In fact, I just want to do that. Just to show you it's going to make sense of this thing. So 5 times 1.8 to the power of 2. And that gives us 16.2. So that goes up. Again, it's going to be an 80% increase is what that is. An 80% increase. If you're multiplying something by 1.8, it represents an 80% increase because 80% is 0.8. If it were just multiplied by 1, it would be a 0% increase. So it's a little bit complicated there, but it's not going up at all. You're just going to get 5, basically, if you're multiplying by 1. But you're multiplied by 1.8, that's 80% more than 1, so that's going to give you an 80% increase. Does that make a little bit of sense?
Yes.
Okay. And I just noticed here I had this multiplied by 1 instead of raised to the power of 1, but that gives us the same thing. That was still 9 there. But when you see, especially with these percent increase and decrease questions, we'll see some more coming up. When you start plugging in values for the variables, it just starts making sense. And you can interpret what things mean if you do that. Any questions before we move on?
No.
Okay.
Nope.
All right. All right. All right, Emma, go and read question number 3 for us, please, when you see it on the screen.
X squared over 25 equals 36. What is the solution to the given equation?
Ooh, what are we solving for here, Emma?
I guess we're solving for X.
Yeah, we're solving for X, the solution to the equation.
Yeah.
And there's an algebraic way to do this. We could do it. It's not too complicated. But do you see how we can just plug in these values from the answer choices in for X and see which one gives us a true statement?
Mm-hmm.
That's the easier path here. Don't be an algebra hero. I mean, you can do it. You might look at this and be like, I can do the algebra here. Man, it's just set up perfectly for plugging in values. Just plug those in for X and let's see what happens. So let's start with answer choice A. And you might be able to look at that mentally and see if that's going to give us a true statement. Will that give us a true statement if we plug in a 6 for X? Do you have any idea? And you can use the calculator if we need to. You want to use the calculator? Let's punch it in. We'll get 6 squared divided by 25. And if that gives us 36, it's the right answer. Does that give us 36?
It doesn't.
No way. Not even like 1.44.
Yeah.
Right. I mean, 6 squared is going to be 36. We'll get 36 divided by 25. So that doesn't make a ton of sense. Let's test answer choice B. And again, this is where like you're just using the Desmos, especially with plugging in, is so easy because I'm just going to leave that expression here and replace the 6 with a 30, and we'll see what happens. Does that give us a true statement? Does that give us 36?
I can't tell.
Are you looking on the screen share?
Sorry. Yeah, I screen share.
So I punched in 30 for x. So we're squaring the 30 and dividing it by 25.
Okay.
Does that give us 36? It tells us right here in Desmos.
Yes.
Do you see it?
Yeah.
Yeah, it gives us 36. There's our answer. That's all you need. Answer choice B. Does that make some sense?
Yes.
Yeah. Yeah. And then 450 and 900 is just going to be way too big. Those aren't going to work. You could test them if you wanted to, but I mean, you got a true statement here, so I think we're good stopping at B. Any questions about that or no?
Nope.
Okay. Okay. There is another way to solve this. You could graph this as well in Desmos, kind of using the strategy we used in the last session, right? You could subtract 36 from both sides and graph it and see what the solutions are. That would work as well. You could do that. But this one's just set up perfectly for just plugging those values and just testing them. Just turn it to arithmetic, see what works. All right. All right, Catherine, I think you are up. Go ahead and read question number 6 for us, please. Want to see it on the screen?
Don't we read the equation as well, or
No, just read the question. That's good enough.
what is one possible solution to the given equation?
Okay, we're looking for a possible solution. Is that pretty clear, Catherine?
Yes.
Yeah.
it is.
Okay. Good. Now, notice we got these funky bars here in this question. Have you seen those bars before? Do you know what that means?
Yes.
Yeah,
It's asking for the absolute value.
Absolute value. Yeah. So you would read that as the absolute value of x minus 5 equals 10. Okay. How comfortable are you with operations with absolute value, especially with equations? Are you relatively comfortable with it or not so much?
Kind of. Looked at that before.
That's kind of how most students feel. They're like, I kind of know what that means, but I'm not super certain. And then they don't quite know what to do with it with equations. Okay. And I'll be honest, like, I'm not 100% certain. I think I can figure it out. But like, I'm just kind of iffy about it. And it's just always kind of confusing dealing with absolute value in equations. First, let's talk about what absolute value means. I think that's kind of essential to this. So I want to go to the rules real quick. I'm just going to bring this up on my screen share. And I've got basically every concept you need to know on the digital SATs here on this cheat sheet. Absolute value is basic concept I. Can you see that on the screen share, Catherine?
I can.
Yeah, good.
Yeah.
I want you to read that bullet point there for absolute value, please.
Calculate what's inside the bars. If it's positive, keep it positive. If it's negative, make it positive.
Yeah, and then I've got an example there of the absolute value of 3 minus 5 is 2, positive 2.
Mhm.
Because if you calculate what's inside the bars, so you calculate 3 minus 5, what is 3 minus 5, by the way?
-2.
Negative 2. And then if it's positive, you keep it positive, but if it's negative, you make it positive. So it's basically negative 2 made positive, which just becomes positive 2. Does that make sense, Catherine?
Yes, it does.
Ruby, Emma, is that familiar? Absolute value, does that make sense?
Yes.
Yes.
Okay, you got to know it. It does pop up on the digital SAT. So a lot of students think, they misinterpret this. They think, oh, you flip the sign. And that's true if it's negative, you flip the sign. But if it's positive, you don't flip the sign. Basically, whatever comes outside of those absolute value bars has to be positive. That's the idea. So let's go back to the question. Instead of doing an operation here, I think we can just do a lot of logic and kind of test values and figure this thing out. Because there's some number, minus 5, and then we take the absolute value of that number, we get 10. So we know what's inside those bars is going to have to be either 10 or negative 10. It's going to have to be 10 or negative 10 ultimately. Does that make sense, Catherine?
Yes, it does.
Yeah,
Yeah.
because the absolute value of 10 is 10. The absolute value of negative 10 is also 10. So I think we just look at this and play with the numbers and figure out what value of x is going to give us either a 10 or a negative 10 inside the bars. What value of x?
Well, x could be 15.
X could be 15, right? Because 15 minus 5 is 10. So that's one solution. What's another solution?
-5.
Or negative 5, right? Because negative 5 minus 5 is a negative 10. The absolute value of negative 10 is 10. Do you see how you don't have to do any algebra there? You can just apply a lot of logic and kind of figure out what it means.
Mm-hmm.
They'll take either answer, 15 or negative 5. They're both true. Questions about that, Catherine, or no? But do you see how easy it would be to look at that question and be like, oh man, I'm not quite sure what to do, and you try to do like an algebra thing? You might get it, maybe. But if you just plug in the values and turn to arithmetic, and you know what absolute value means, you're basically guaranteed to get it if you can do the arithmetic. Questions about that, or does that make sense?
That makes sense.
Okay, beautiful. Let me show you one more way to do this. I want to bust out the Desmos calculator again. You can actually graph this and apply that strategy we used in the last session, the day 1 session. They give you the absolute value bars here. In Desmos, do you see this? Like, we see the absolute value bars, the absolute value of A. You can punch that in, and you can graph this. We can do x minus 5. And remember, we got to get all the terms on one side of the equation. So we do minus 10. Does that make sense why we do the absolute of x minus 5 minus 10? Does that make sense, Catherine?
To make it 0, yes.
Yeah, to make it 0 on the right-hand side. That's it. So you subtract both sides by 10. And we get this V-shaped graph in Desmos. And if we find the x-intercepts, those are going to be the solutions. So I'm going to zoom in a little bit. Here's one solution right here. What's the x value at that point?
15.
15. What's the x value at this point?
5. Negative 5.
Negative 5, which is what we got as well just by plugging values in place of the variables right off the bat. Does that make some sense?
Yes.
Okay. So you can graph it as well. A couple ways to solve, but don't do the algebra. It's just kind of confusing and it's just easy to mess up. So think in terms of plugging values to the variables or just graph it. Either one works. Any questions?
Nope.
All right. You're doing great. All right, Ruby, you're up. Go ahead and read question number 11 for us, please, when we see it on the screen.
Which expression is equivalent to that?
To that thing, yeah, love it. What are we solving for here, Ruby?
We are solving for, I guess, x on both. Yeah.
Well, there's no equation here.
Yeah.
Right? Which is interesting. So we're not solving for x. Look at the wording here of the question. They say, which expression is equivalent?
Oh, which expression is equivalent to that? Like once we break it down and...
Yeah, if we break this down, really, it's a combining like terms question. If we combine all those terms, there's a way to do it algebraically. We'll talk about it here in just a minute. But one of these answer choices is going to be equivalent or equal to that expression in the question. One of these answer choices is equal to that. Does that make some sense now what the question's asking us?
Yes.
Yeah, we're not solving for x here. It's easy to sort of look at an expression and be like, oh, what's x? But that's not the question. Which is equivalent or equal to. Okay. Now, do you feel pretty comfortable with combining like terms? Like, do you think you could do this algebraically? Yes or no?
I think I probably could, yeah.
I think most students probably could. Most students probably could. This is Ruby, right? You're solving this?
Yes.
Yeah. Catherine, Emma, would you feel comfortable solving this by combining like terms?
Kind of.
Kind of?
Yeah, it just takes a while.
Okay.
Yeah.
It's not too bad. We'll talk about it here in just a minute. Let me show you one strategy, especially if you're kind of iffy about this. And this strategy really shines on the higher level difficulty questions where combining like terms is not even slightly obvious. We can plug in values for the variables here. We can plug in a value for x into this expression right here. We'll find out what that expression equals for some value of x. And we'll pick a real simple value like 1, or you could do 0 as well, potentially. I don't think that's going to help here. We'll do 1. We'll make x equal 1. Plug in a 1 for x into the expression in the question. We'll find out what that equals when x is 1. And then we'll plug the same value into the answer choices. And the right answer is going to match up with the value we got for the expression in the question for some value of x, if it's equivalent. Does that make a little bit of sense, Ruby, why that's going to work?
Yes, that makes a lot of sense.
Yeah. So we're just turn this into arithmetic, thinking in concrete terms and just avoiding the algebra. So let's practice it. And if it's not super obvious to you yet, it will be here in just a moment why this works. So let's plug in a 1 to the expression in the question. Now, you could use Desmos here to keep it, like just in case you're worried about messing up the arithmetic somewhere. I'll bet we could apply a lot of logic and just some basic estimation to figure this out. Because the beauty of plugging in a 1 for x is that x to the power, 1 to the power of anything is just 1. Does that make some sense? Why 1 to the power of anything is 1? Like 1 to the power of 3 is just 1.
Yes.
Yeah. So for the first terms in parentheses, we're just going to get 7 times 1 plus 7 times 1. Does that make sense?
Mm-hmm.
And what does that give us?
Just 7 plus 7, so 14.
Yeah, we get 14, right, for the first set of terms in parentheses. Catherine, Emma, does that make sense why we get 14 for this first set of terms in parentheses?
Yes.
Yeah. Okay, great. This is the beauty of plugging in a 1, right? Zeros are also great. Although I think if we plugged in 0, everything would be 0 if we plugged in 0. So it makes more sense to start with 1 here. We get 14 minus, and then look at the second set of terms in parentheses. We've got, notice x is raised to the power of 3 again. So 1 to the power of 3 is still going to be 1. So you're just going to get 6 minus 3. What's 6 minus 3, Ruby?
3.
It's going to be 3. So we get 14 minus 3. What's 14 minus 3? You don't even need Desmos here. What
11.
It's going to be 11. So when x is 1, the expression of the question equals 11. Is that clear, Ruby?
Yes.
Catherine, Emma, is that clear?
Yes.
Okay, great. All right, let's plug in that 1 for x into the answer choices. The right answer choice has to give us 11. And I'll bet you can just look at these, even without using Desmos. You could, but just look at answer choice A. Is that going to give us 11, Ruby?
Yes.
Heck yeah, it is, because we're going to get 1 plus 10.
Mm-hmm.
So it could be A. Okay, now here's the deal. When you're plugging in values, you got to test all the answer choices. Because they're, the makers of the test, they know this is one of the most useful, most powerful strategies there is for the digital SAT. So they're designing the answer choices sort of based on that understanding, that assumption students are going to do this. So there could be multiple answer choices that give us a true statement. So we can't stop when we see something that looks good. We got to test them all. But look at answer choice B, Ruby. Is that going to give us 11?
No.
No. What does that give us?
That's going to give us -3.
It's going to give us -3. Yeah, because you get -13 plus 10. That's -3. And again, if you weren't sure about the arithmetic there, just punch it into Desmos. That's going to be -3. So we know it's not B. What about answer choice C? Is that going to give us 11?
No, that gives us -9.
-9. That's not going to work. What about D? What's that going to give us?
That gives us 5.
Yeah, it gives us 5. It gives us 1 plus 4. So it can't be D. It's got to be A. Whee! Any questions about that, Ruby?
No.
Okay. Catherine, Emma, questions about that or no?
Nope.
Most of the time, when you see that phrasing, the equivalent expression, which is an equivalent expression, there's a way to plug in values. It's not always the easiest way to do it. And if you're really comfortable with combining like terms, again, you can do the algebra here. I'm not opposed to it, but boy, if you can plug in a value, you're going to get it. It's going to work. So, and even if you're iffy about the arithmetic, just punch into Desmos and you'll be good. Let's talk about the algebra a little bit real quick. I want to show you why it's A from an algebraic perspective. Okay. Notice that if we're doing the algebra on this, we've got to distribute that negative sign here in the expression of the question. Is that pretty clear, Ruby? Does it make sense we have to distribute that? Yeah, because you're subtracting all that stuff in parentheses. So if you're working this out algebraically, it's got to be 7 times x to the power of 3 plus 7x minus 6x to the power of 3 plus 3x. Does that make sense why we're flipping that sign there from the -3x to plus 3x? Does that make sense?
Yes.
So we're just distributing that negative sign to both of those terms. Right here. And right here. Okay. And then it's just a question of combining like terms. Do you see terms here that are like? That is, they have the exact same variables and the exact same exponents. Do you see any terms that are like?
Yes, so like 7x and 3x.
Yeah, the 7x and the 3x, we can combine those. And what does that give us combined?
That's going to give us 10x.
10x, right? Yeah, you're just adding the coefficients in front of the variables, keeping the variable. That's 10x. Those guys are gone right there. And then the other two of these guys right here, what are those combined?
That's just going to give us 1, so it'll be just x to the... Oh, I always get confused on how to say this correctly.
Yeah, to the power of 3 or cubed, yeah.
To the power of 3,
yeah. So you could describe it as 1 times x to the power of 3 or just x to the power of 3 because it's the same thing. That's answer choice A. Does that make sense?
Mm-hmm.
So that's not too bad either. I just want to talk about combining like terms a little bit. Sometimes that's helpful to do. But you can also plug in values in place of the variables. That works as well. Which method do you prefer, Ruby? Plugging in values or doing the algebra on this?
Probably plugging in values just because I feel like it's just easier for me to remember.
Yeah, if you can do the arithmetic, you're going to get it right. So look for ways to plug in values on these equivalent expression questions. Great job. All right, I think we got another equivalent expression question coming up right now. Oh, this one's tricky. This one's very tricky. I'll guide you through it. Emma, go ahead and read question number 19 for us, please, when you see it on the screen.
Which expression is equivalent to
to that. Yeah. So I'd read that as a to the power of 11 over 12.
Yeah.
Is how I'd read that. Yikes. And that's where a is greater than 0, apparently. I'm guessing you're not super familiar with fractional exponents. Most students aren't. Are you familiar with fractional exponents or no?
Yeah.
A little
somewhat.
bit? Yeah. Are you familiar with, look at these answer choices. You're familiar with this notation here of like these crazy roots. Like we got some to root 12 and root 144 and root 121. Have you
Not
seen that
that
stuff?
big.
What's that? Yeah, not that big. Yeah. Maybe like a cubed root, the root 3 or something like that.
Yeah.
Like root 144. It's just intimidating. This is just an intimidating looking question because most students aren't familiar with fractional exponents. Most students aren't super familiar with roots, especially to these big numbers here. I mean, is it obvious to you what the right answer is, kind of thinking in algebraic terms, or not so much? You can say no if it's not. And maybe it is to you.
Not really.
Yeah. What about you, Catherine or Ruby? Do you think you know what the right answer is, sort of thinking in terms of like the properties of exponents? Is it obvious to you or no?
Would it be B?
I'm not sure. It might be. I'm not even certain right now. I've got the answers here, but I'm not looking at them right now.
Yeah.
We're going to find out. We're going to find it because you don't have to guess. We're going to use that strategy of plugging in values in place of the variables. We're going to create a value for A. And we're going to plug that value for A into the expression of the question. And we're going to plug that same value into the answer choices. And the right answer is going to match up for some value of A. Does that make sense, Emma, why that's going to work?
Yes.
Okay. Now, what value of A do we pick? We're talking about zeros and ones are great in general, but that's not going to work here, right? Because if we've got 0 to the power of anything is 0. So everything's going to be 0 if we make A 0. And 1's not going to work either because 1 to the power of anything is 1. So we've got to make it a little bit bigger. But I think if we make A 2, that's going to help us distinguish between the answer choices. Does that make sense why 2 here is better than a 0 or a 1? Does that make some sense, Emma?
Yes.
Yeah, there's a little art to plugging. I mean, you could try a 1, but again, everything's going to be 1 if A is 1. But if we make it 2, that's going to help us differentiate between the answer choices. Let's use Desmos here, because I'm not sure, just looking at that, I'm not sure what 2 to the power of 11 over 12 is. I have no idea. I'm still not sure. Let's just punch it into Desmos. And you can do fractional exponents in Desmos. You can. Can you see Desmos on the screen share, Emma?
Yes.
Okay, great. So I'm punching in 2 to the power of 11 divided by 12. You can do fractional exponents in Desmos, no problem. Do you see what that gives us?
Yes.
Yeah, we got like 1.887 something. Okay, I'm just going to make a note of that here on the whiteboard. We got 1.8877 something or other. Okay. So that's what the expression of the question equals when A is 2. Any questions about that, or is that pretty clear?
That's clear.
Okay, great. Okay. Now let's test these answer choices. Okay. Now we got to be able to navigate Desmos here because there is a way to do these like weird roots in Desmos. And you got to go to that functions button here. And if you scroll all the way to the bottom of the functions, all the way to the bottom, and it's one of the last buttons there, you see this like root N button at the very bottom. And everybody else, Catherine and Ruby, I want you to go to Desmos and find this button just so you can see where it is, because this is really helpful on a number of questions with weird roots. Okay. And if we click that button, we can adjust what the root is going to be. So to test answer choice A, I'm going to make the root 12. And I'm going to just punch it into Desmos. I want everybody to try that on your own. Anybody watching the recording as well, just play around with Desmos, see if you can find that button and practice punching this in. And we're still plugging in a 2 for A. So it's going to be 2 to the power of 132. If that gives us 1.887, we're good. But it doesn't. We get like 2048. Emma, is that clear? Why answer choice A is not correct? You don't have to think about it too much. You don't have to try to interpret the fractional exponent. You don't have to try to interpret the roots or any of that stuff. All you're doing is just punching in Desmos and seeing what matches. All right. Let's try answer choice B. And we'll do the same thing here. Use that function button. And here, what's the root for answer choice B? Do you understand my question?
The answer choice B?
Yeah, answer choice B.
It's equivalent.
Well, you plugged it into Desmos already?
Yeah.
Yeah, it's 144, and then it's 2 to the power of 132. Oops, I did 2 squared. Hold on. 2 to the power of 132. Oh, looky at that. That works. 1.887. Mm-hmm. And that's it. Well, actually, no. Let's test the others. Let's test the others. I do want to test the others just to make sure. That's looking good. Let's, I'm just going to punch this into Desmos here. Answer choice C. That's 121. 2 to the power of 132. Is that equivalent? Answer choice C?
No.
No, it is not. Let's try answer choice D. All right. 11. 2 to the power of 132. Not equivalent. So it does have to be B. And it is. Any questions about that, Emma?
No.
Okay. Catherine, Ruby, any questions about that question?
No.
No. By far, the easiest way to do it is just plugging in values. There's like no interpretation necessary there at all. I mean, if you're really comfortable with fractional exponents and really comfortable with these roots, you can do it. There's a way to do it. It's not too terrible. But I say just plug in values for the variables. All right. And Catherine, I think you are up next. Go and read question number 22 for us, please.
Got it. Two variables, x and y, are related such that for each increase of 1 in the value of x, the value of y increases by a factor of 4. When x equals 0, y equals 200. Which equation represents this relationship?
Ooh, Catherine, what are we solving for here with this question?
So we're solving for an equation in like through A through D that represents the relationship when x equals 0, y equals 200.
Yeah. Now, I don't think it's super obvious just looking at the answer choices what the right answer is. Maybe it is to you. I mean, do you think you know what it is just by looking at the answer choices? Yeah. Ruby, Emma, is it obvious to you looking at this and thinking in sort of algebraic terms what the right answer is?
No.
Yeah.
No.
Yeah.
Not at all.
It's just not. Don't try to interpret these answer choices. Like, don't try to be like, oh, if I think about it the right way, I'll figure it out. It's like, no. Just plug in values for the variables. Let's think in concrete terms. Turn this thing into arithmetic. Because we know when x is 0, Catherine, what does the y value have to be?
200.
It's got to be 200. So let's just plug in a 0 for x and see which answer choice gives us a 200. Does that make sense?
Mm-hmm.
Let's just use Desmos. Let's do it. Let me clear this out. And we're going to punch this in. So it's going to be 4 times, and what's our x value again?
0.
0. 4 times 0 to the power of 200. And what does that give us?
0.
That gives us 0. So what do you think about answer choice A?
No.
No, right? Because the right answer's got to give us 200 for y. Does that make sense?
Yes.
That's not A. Just arithmetic. That's all you need here. And Desmos. Let's punch in answer choice B. That's going to be 4 times 200 to the power of what?
0.
0. X is still 0. What does that give us?
4.
So what do you think about answer choice B?
Nope.
No, because we're looking for 200 for y. Let's try answer choice C. A little different here. This is 200 times 0 to the power of 4. What does that give us?
0.
0. So it's probably not answer choice C. I sure hope answer choice D works. 200 times 4 to the power of 0. How's that?
Yep.
That gives us 200. That's what we're looking for. It's got to be D. Questions about that question?
Nope.
Don't try to interpret these expressions. They tell us when x is 0, y's got to be 200. They tell us that. Just punch in the numbers and then use the Desmos. But it should make sense. We were just talking about things to the power of 0. What do things to the power of 0 equal? Catherine, what do they always equal? What's anything to the power of 0?
1.
1. So if you look at answer choice D, it makes a ton of sense because we're going to get, when x is 0, we're going to get 200 times 1, which is just 200. Does that make sense why it is answer choice D? From
Yes,
an
it
algebraic
does.
perspective, yeah. But again, you don't even need to go into those, think of those terms. You just punch it in. make it concrete. Any questions about that?
Nope.
Okay. All right, just a few more plug-in the values questions. We'll take a break here as soon as we can. I'll try to go through these pretty quickly here. Go and read number 12 for us, please, Ruby, when you see that on the screen.
An object is kicked from a platform. The equation, that thing, represents the situation where meters t second. Wait, I just skipped something. Sorry. Where h is the height of the object above the ground in meters, t seconds after it is kicked. Which number represents the height in meters from which the object was kicked?
What are we solving for here, Ruby?
We are solving for the number which represents the height.
Yeah, what number represents the height of the object, the height from which the object was kicked? It's kind of specific here. Does that question make some sense?
I think so.
Yeah, I mean, so we've got like some balls being kicked off a platform, right? And and then we got some expression representing the situation, and we got to figure out what's the height when the object was kicked. Now, I'm guessing it's not obvious, kind of looking at this equation, what that is, like what the height is. When, right. It's like I got a bunch of numbers here. What does it all mean? It's just not super obvious. It's not. This is a really tough question. We're just trying to interpret that expression. It's just not obvious at all. But here's what we're going to do. We're going to plug in a value for t, which is going to make this really, really easy. Okay? Because they're asking for, okay, what's the height when the object was kicked? We know the t value when the object was kicked. The moment it was kicked, we know the t value. What's the t value, Ruby, when the object was kicked? Think about it. If it's t seconds after it was kicked, what's the t value the moment the object is kicked? The t value is 0. Is that clear?
Yes.
It has to be. Catherine, Emma, does that make sense? Why the t value is 0 when the object was kicked?
Yes.
Good. Yeah. You've got to make that connection. I've seen a lot of questions like this on the SAT and digital SAT. They like these kind of situations. But if you can draw out that information, which you can, then we're just plugging in values here. That's all we're doing. The t value, if we plug in a t for 0, we're going to get the height when t is 0. That is the height when the object was kicked. We could use Desmos if we want to. We could kind of work this out on the whiteboard, but I don't think we need to, because anything times 0 is 0. So if we plug in a 0 for t into that expression, what's the height of the object when it was kicked, Ruby?
It's just going to be 0.
Well, no. Maybe we should plug it in. Maybe
we
should
it's going to be 9. It's going to be 9.
It's going to be 9. Is that clear why it's going to be 9, Ruby?
Yeah,
That's all right, because these terms here are going to become 0.
Yeah, because of the t. Yeah, 9 doesn't have a 0.
But we're left with the 9 because and that's it. And again, if you wanted, you could punch it in Desmos to make it really, really clear, in case there was any confusion.
Yeah, no, I see that. I just
gotcha. So be careful there.
Yeah.
So what's the right answer here?
9.
It's 9. It's D. No operation there. Nothing to interpret. Just thinking in concrete terms and plugging in values, and you got your answer. Is that pretty clear, Ruby?
Yes.
Okay. Another way to do this too, you could graph this equation in Desmos and you kind of see the situation. In fact, I'm going to do that real fast. And sometimes just graphing the equation can help you sort of interpret what's going on. So I punch this in Desmos. We'll get negative 4.9 times x squared. I'm just going to replace the t's with an x. Times 7x plus 9. Zoom in. And then we get a parabola sort of describing the situation. Here's where the t value or the x value is 0. It's right here. So here's where the ball is kicked, right? That's where it starts. And it's kicked up in the air and then kind of falls down here. Do you see that? There's sort of like a trajectory of a ball being kicked, starting here, going up and then going down. Does that make some sense, Ruby?
Yes.
So the parabola also shows us. And then if they were asking about like the maximum height of the ball, we could find it right here. Here's the maximum height. It's going to be 11.5 meters. Does that make sense? If they asked us for the maximum height, we can also just graph it and find it. Or if they asked us for like, what's the time when the ball hits the ground? That's just this spot right here. So that'd be like
Okay.
2.246 seconds. I just want to point that out because you could see some questions like this too, where like it may not be super obvious, just by looking at the equation. We can graph it. You can sort of interpret what things mean if you graph it as well. Okay. But if we look at the moment when the ball's kicked, here's the moment. That's the height of the platform. It's 9 meters. That also works. Questions about that?
No.
Okay. But again, like, I mean, are there any algebraic operations to do here on these questions or no? I mean, we're not doing like step-by-step operations here. That's the majority of questions. There's a handful on every test where you do have to, but it's a small minority of the questions. All right. All right, Emma, go ahead and read question number 25 for us, please, when you see it on the screen.
Okay. A model estimates that at the end of each year from 2015 to 2020, the number of squirrels in a population was 150% more than the number of squirrels in the population at the end of the previous year. The model estimates that at the end of 2016, there were 180 squirrels in the population. Which of the following equations represents this model, where n is the estimated number of squirrels in the population t years after the end of 2015, and
T is less, it's less than or equal to.
Less than or equal to.
Yeah, 5. Whoa, what are we solving for here? Emma, any idea?
You
can say no if you don't.
I guess we're just trying to find which equation represents the entire, all the words they said.
All the stuff, yeah. All the stuff. Which equation represents the situation? Yeah.
Yeah.
There's a lot of information here, right? It says, from 2015 to 2020, the number of squirrels in the population is 150% more than the number of squirrels in the population at the end of the previous year. So it's like, it's going up by 150% every year. Does that make some sense?
Yes.
Okay. And we know also, they say at the end of 2016, there's 180 squirrels in the population. That's good enough to find the answer here, because at the end of 2016, we know what the t value is at the end of 2016. What's the t value at the end of 2016?
I guess it'd be a 1.
Yeah, the t value is 1.
Yeah.
Does that make sense? Why at the end of 2016, the t value is 1. One year's passed.
Yeah.
Okay. That's it. Okay, great. So if we plug in a 1 for t into the expressions in the question, the right answer has to give us what?
180.
Has to give us 180. That's what we're looking for. Does that make sense?
Yes.
Because that's what the question says. It says at the end of 2016, there's 180 squirrels in there. And at the end of 2016, the t-value is 1. So we just punch these into Desmos. There's no interpretation necessary here. Just make it concrete. Look at answer choice A. We're going to punch that in. We get 72 times 1.5 to the power of what?
The power of 1.
The power of 1. Does that give us 180?
No.
No way. 108. Not big enough. Let's try answer choice D. 72 times 2.5 to the power of 1 still, which is just going to be 2.5, right? What does that give us?
Hold on.
You punching it on your end?
I put it in wrong. 180.
It gives us 180. That's looking pretty good. Okay, let's keep testing other answer choices though. It could be B. We know it's not A for sure. Let's plug into C. Let's just see what happens. But I don't think it's looking very good. 5. 1. Is that 180?
No.
No. And then D's not. Is it clear D's not going to work? Right?
Yes.
Like just looking at him, right? You're going to get 180 times something bigger than 1. It's going to be bigger than 180. That's not going to work. So it's answer choice B. Any questions about that, Emma? Or does that make sense?
No.
Yeah. Don't try to interpret this. And by the way, like just looking at it, like everybody's going to pick A. You know what I'm saying?
Yeah.
Like you're like, oh, well, 1.5, that's 150%, or like, it's just easy to misinterpret that. Mm-hmm. It's just not obvious at all that it's You're multiplying by 2.5 here. It's not, but it is. If you're multiplying by 2.5, that represents a 150% increase.
Yeah.
If you're multiplying by 1.5, that represents a 50% increase, not a 150% increase. Does that make sense?
Yeah. Yes.
Yeah. But don't even try to interpret it. You're trying to interpret it. It's just so easy to mess up. Just think in concrete terms, plug in values for the variables. Now, again, you got to figure out, okay, what value you're plugging in for t, but it's not that complicated.
Yeah.
It's not. You just got to think about it the right way, but think in concrete terms. That's the easiest path. This is a tough question. Very few students are going to get this right. When you plug in values, you got it. All right. We'll do this real fast. These next questions we'll get through as fast as we can here. And Catherine, I think you are up. Are you still with us, Catherine?
I am.
You are? Okay, great. Go and read question number 4 for us, please. We'll do this real fast.
Okay. What is the solution, XY, what's the solution to the given system of equations?
Okay, we're trying to solve, right? We're trying to find the solution, XY, to the system of equations here. You could do the algebra on here. It's not too bad. Would you feel comfortable with the algebra or not so much?
I think in this one, it doesn't seem too hard.
It's not too bad. You could totally do it. But there's an easier way to do it. Do you see the easier way to do it here by plugging in values for the variables? Is that clear?
Mm-hmm.
I mean, look at the answer choices. They give us these XY pairs right here.
Yeah.
We can just plug those in, and the right answer's got to give us a true statement for both equations. Does that make sense, Catherine?
Yes, it does.
That's just the easiest path. Don't try to be an algebra here. I see students make a lot of operational errors on systems of equations, even if you kind of know what you're doing. Just try some arithmetic. Now, if you look at these answer choices, all of them give you a true statement for the top equation. I'll just tell you right now. Is that pretty clear? Like if you add the x and y values, you get 18 for all the answer choices. Does that make sense?
Yes, yeah.
So you got to really plug into the bottom equation here. But look at answer choice A. If we plug in a 15 for x and a 3 for y, does that give us a true statement?
Yes.
Heck yeah, it does. What about answer choice B? If you plug in... No, that doesn't give us... Is that clear? Ruby and Emma, is that clear as well? Answer choice B does not give us a true statement. When y is 2, x is just not 16. What about C? Is that going to give us a true statement? Catherine?
No, it's not.
No, it's not. What about answer choice D? Is that going to give us a true statement?
Nope.
No, it's not. It's answer choice A. Do you see how much faster and easier that is if you just plug in the values in place of the variables? Is that clear?
Yeah.
Okay. Now, of course, we could also solve this using Desmos. Do you see how to do that as well?
Yes. Just like... Yeah.
Just graph them and the intersections can be the solution. That works too. Don't be an algebra hero. It's going to be faster, plug in the values or graphing. You're going to get it. Okay. Now, I've got 2 more system equations questions coming up. We'll take a little break here in just a moment. But I want to start with that one to show you can always, or often at least, plug in values for the variables, especially if they give you the XY values. This is not obvious that this is a plugging in values question because we don't see any variables here, but we're going to test the answer choices here and treat it like a plugging in values question. Ruby, go and read question number 18 for us, please.
Okay. A company that provides whale watching tours takes groups of 21 people at a time. The company's revenue is $80 per adult and $60 per child. If the company's revenue for one group consisting of adults and children was $1,440, how many people in the group were children?
What are we solving for here, Ruby?
We are solving for how many people in the group were children.
How many people in the group were children? That's what we're solving for. And they give us 4 possible answer choices. These are the possible number of children in the group.
Mm-hmm.
Does that make some sense?
Yeah.
Okay, good. Now, of course, is it obvious to you that this is a system of equations question, like they want you to develop 2 equations with 2 unknowns? Is that obvious or no? Maybe it's not.
No, not really.
Okay, yeah, that's what they're asking you to do here. That's kind of, if you look at the answer explanations, they want you to set it up. Because we've got some unknown number of children, some unknown number of adults. And we know altogether it's got to add up to like $1,440. And then there's like, the tickets are $80 per adult, $60 per child. We could set up 2 equations. Don't even go there. Right? I just see students mess up the operations on systems of equations more often than not. And there's a way to just test the answer choices and turn this into arithmetic. It's much easier. Okay? Because we know if there's 3 children, look at answer choice A. If there's 3 children, these are the kids right here, children. We know how many adults there are if there's 3 children. How many adults are there if there's 3 children?
There are 18
18,
adults.
because they got to add up to 21. Does that make sense?
Mm-hmm.
Now we know the cost of ticket per adult. We know the cost of tickets per child. We can test these answer choices and see which one gives us 1,440. Does that make sense? How you can just turn this into arithmetic here?
Yes, yeah.
Let's do it. I'm going to bring up Desmos. That's probably the easiest way to do it. So here's what it's going to look like. It's going to look like 3 times, and then what's the cost of the tickets for children?
It is $60 per child.
So it's 3 times 60. Does that make sense? That's the tickets, or the amount of money from the kids. And we'll add that to the amount of money from the adults. And we've got 18 adults, so it's 18 times what?
18 times 80.
80, because that's the cost of tickets per adult. Does that give us 1,440?
No.
No, it does not. That's not going to work. It's not answer choice A. Does that make sense how we can test these answer choices here?
Yeah.
Let's try answer choice B. All right. If there's 9 children, how many adults are there?
There are 12.
12 adults. Let's test it. I'm just replacing the 3 with a 9. I'm going to replace the 18 with a 12. Does that give us 1,440?
Nope.
No, it does not. We've got 1,500 there, so it's not B. Let's try C. If there are 12 children, how many adults are there?
There are 9.
9 adults. So I'm replacing the 9 with the 12. 12 kids. 9 adults at $80 a ticket. Did that give us 1,440?
Yes.
Heck yeah, it does. Answer choice C. Oh yeah. Any questions about that question?
No, that makes sense.
Look for ways to test answer choices, especially if they're trying to give you a system of equations question. There's generally a way to test them. Okay. Potentially, if you wanted to structure these equations, you could, and then you could graph them. That might work as well, potentially. We don't have time to go over that right now. That could work. Does that make sense? How if you structure the equations, you could also graph them in Desmos? Does that make sense?
Yes. Yeah,
okay. Yeah. Catherine, Emma, any questions about that, or does that make sense?
That makes sense.
Okay.
Makes sense.
Okay. It's the fastest way to do it. You're going to get it if you can test the answer choices. One more question, and we'll take a little break here. And this is similar here. This is another system of equations question. Very tough to do if you're trying to do the algebra here. Very tough. Much easier if you're testing values. I think that was, Ruby, you did the last one. Is that correct? Was that you, Ruby? Maybe not?
Yes, I did.
Yeah, okay. All right. Emma, you are up. Go and read number 18 for us, please.
The product of 2 positive integers is 546. If the first integer is 11 greater than twice the second integer, what is the smaller of the 2 integers?
What are we solving for here, Emma?
Just to find the smaller integer.
Yeah, to find a smaller integer. Remember, integer means a whole number, essentially.
Yes.
So we've got 2 integers, and the product of those 2 integers. So what does product mean? Let's talk about the vocab here. What does product mean?
The product is like the result of multiplying.
Multiplying, yeah. So we multiply these 2 numbers, we get 546. But the first integer is 11 greater, 11 more than twice the second integer. This is a lot to wrap your head around. Does it make sense why they're kind of testing on a system of equations here as well, kind of like in the last question, even though we don't see like X and Y variables? That's kind of what they're dealing with here. Does that make sense? Yeah. And you could structure. We'll talk about that in just a minute as well. But we can just test these answer choices just like on the last one. Okay? Because let's assume that the smaller integer, look at these answer choices. Let's assume the smaller integer is 7. Let's assume that. We can figure out what the bigger integer is going to be if the smaller integer is 7. It's just going to be 11 greater than twice the first one. Does that make sense?
Yes.
Okay. All right. What's 11 greater than twice 7? Do you have any idea?
11 greater than twice 7 is 25.
Should be 25. Yeah. And if we're, unsure about that, you can, again, turn it to, use Desmos. So, 11 greater than twice the second integer. So twice 7 would be 14. It's just going to be 14, twice 7 here, 2 times 7. And then plus 11. Does that make sense? Yeah, it's 25. Does that make sense?
Yes.
Okay. Now we've got our two integers, right? The smaller one would be 7, the bigger one would be 25. All right. In fact, like all the answers here, these are going to be the smaller integers because the bigger one is going to be twice the smaller one plus 11 for all of them. Does that make sense?
Okay.
Yeah.
Yes.
Yeah. All right. So what's 7 times 25? Let's just see. If that's 546, we got our answer. Does that make sense?
Oh, okay.
Yeah. So 7 times 25. I don't think it's going to work. Nah. We got 175.
Okay.
So it's not answer choice A. Yeah, that's not it. Let's try answer choice B. So if the smaller integer is 14, what's the other integer? It's going to be 11 more than twice the first one, right?
Yes.
So it should be 2 times 14.
Times 14, okay.
Plus 11. Does that make sense? What's that give us?
Is it equal to 39?
39, absolutely. All right.
Okay.
Do you see how we can test it?
Yes.
So we're just going to test. We're going to multiply 39 times 14. What does that give us?
546.
546. We got our answer. Answer choice B. This is an example where you can, if you got the right answer, you can stop here, right? Because if 14 works, the others just aren't going to work. I mean, they're going to be way bigger than 546 when you multiply them, right? Because we're going to get like twice 39 plus 11 and then multiply that by 39, whatever that is. They're going to be too big. So we can stop there. Does that make some sense?
Yes.
Okay. Much easier than trying to set up the system of equations here. You got to practice this because you're not really taught this way in math class. You know what I'm saying? Like, there's like, you do the operations and go through all the steps. And you can do that. You can, but you're just much more likely to get it by testing answers, turning everything to arithmetic if you can. Questions about this?
Nope.
Okay. I would love, boy, I just want to point this out. If you wanted to set up the equations, you could. It's just going to be x times y equals 546. And then like x equals 2y plus 11. And there's your two equations. And you could graph them. And you get your x and y values. That would also work. Does that make a little bit of sense how you could set it up and graph it too?
Yes.
It's not a bad way to do it if you can structure the equation. But you can also just turn it to arithmetic.